Hello everyone, I am Agando Amin. I represent Al Malik Saadi University and I am from Morocco. First of all, I would like to thank you all for organizing this conference and I am very proud to be a part of it. My presentation is supervised by Mr. Abdullah Al-Mnia in collaboration with Mr. Muhammad Yasir Noor, titled Learning Shopware Subdivision Parameters for High-Fidelity 3D Reconstruction in Medical Imaging. After the introduction, I will be to start by classical subdivision schemes, then non-uniform subdivision scheme, then convolution neural network, and the important paragraph is experimental result, and finally conclusion. We start by introduction. Subdivision schemes are powerful tools for generating smooth shapes from discrete control points. Chaikin's scheme is one of the simplest and often used as a baseline in geometric modeling. However, classical schemes rely on fixed parameters which limit their ability to adapt to complex structure. In this presentation, we introduce an adaptive approach based on machine learning to improve 3D reconstruction, especially in the medical field. We move now to paragraph of classical subdivision schemes. Chaikin's algorithm is a corner-cutting subdivision scheme introduced in 1974. It generates smooth curve by refining the polygon chain. At each interaction, new points are inserted by cutting corner. Given control point Pi, it creates new point. By this operation, the limit curve is class 1 continuous B-spline of degree 2. This figure explains Chaikin's subdivision process. You can see here we have square control polygon and subdivision step 1, step 2, and final subdivision. We move now to Catmull-Clark subdivision schemes. Catmull-Clark is a surface subdivision scheme developed in 1978. It generalizes Chaikin's scheme from curves to polygon meshes. The algorithm works by refining each face into smaller quadrilaterals. New points are computed as weighted averages of surrounding vertices, edges, and faces. The resulting surface is class 2 continuous almost everywhere, producing smooth and visually pleasing results. It supports arbitrary topology and is widely used in three-dimensional modeling and animation. In this figure, we represent the Catmull-Clark subdivision process. We start by the cube plus mini subdivision to have this form reality. We move now to non-uniform subdivision scheme. Non-uniform subdivision scheme. Non-uniform subdivision schemes adapt to refinement rule locally using a tension parameter UI specific to each segment. This is the formula of non-uniform subdivision schemes. We have a type for subdivision non-uniform, for example, trigonometric subdivision scheme. The scheme uses a trigonometric function to calculate the tension UI, resulting in smoother and more periodic curves. This is the tension of parameter, the value of tension of parameter. And this is the role of subdivision. We move now to the second example for non-uniform subdivision. This is hyperbolic subdivision scheme. This scheme uses a hyperbolic function to increase the local tension, creating sharper transition and tighter curvature control. This is the UI, the tension of parameter for hyperbolic subdivision schemes, and this is the rule of this subdivision. We have here in this figure effect of tension parameter on curve sharper. In the middle, this is the control polygon of rectangle, and in the right, we have the subdivision hyperbolic. We used the parameter of tension superior than 1. And in the left, we have the subdivision trigonometric. We used the parameter of tension inferior than 1. This is a comparison of the subdivision trigonometric and the subdivision hyperbolic. It means non-uniform subdivision. Here in this figure, as you can see, this is the Chaikin subdivision. It means the uniform subdivision scheme. In the right, we have this figure represent trigonometric subdivision. We used U parameter of tension equal 0.4. It means the parameter of tension trigonometric. And in the left, this figure represents hyperbolic subdivision. We use the parameter of tension equal 4. This is the Vizier comparison of subdivision schemes, Chaikin with the non-uniform. Two examples of our non-uniform. We move now to convolutional neural network, the method of EI. This is the architecture of CNN. We start by input image. It means the parameter of control. Then the convolution layer, Boolean layer, and finally output. It means the image in output. Applying CNN to subdivision schemes. The goal is automatically predict a vector of tension parameter UI for control polygon. Pipeline overview. The control polygon is encoded as a sequence of two-dimensional coordinates. This sequence is fed into a CNN that excretes local geometric feature, angle, and curvature. This network processes these features throughout convolution, activation, and Boolean layers. A flattening operation prepares the data for fully connected layers. Then, dense layers learn to associate geometric partner with the optimal tension values. The output layer products a tension vector UI, which many include value greater than 1. These predicted UI values are then used in non-uniform subdivision schemes, for example, trigonometric or hyperbolic subdivision. The result is smoother data-driven subdivision curve. We move now to the important paragraph is experimental results. Because as you can see here is the figure represent the subdivision Chaikin. It means we used the parameter of tension equal 1. This is the subdivision uniform. And here, this figure represents the subdivision trigonometric. It means we use the parameter of control inferior than 1. And here, we use the parameter of tension superior than 1. It means subdivision hyperbolic. And here, the EI subdivision modeled. We use the parameter of tension equal 1 and the parameter of control superior than 1 and inferior than 1. Optimized tension parameter predicted by CNN. The CNN model predicted a vector of 23 optimized tension parameters UI based on the input control polygon of VART. These values are mostly greater than 1, indicating a non-uniform subdivision with hyperbolic characteristics. This is the predicted values. Applications in medical imaging. Subdivision schemes enhanced by AI are used to reconstruct high-resolution 3D surfaces from low-quality medical data, for example, MRI and CT. These methods improve anatomical structure preservation by adapting the refinement to local geometry. Machine learning models learn optimal subdivision parameters from real medical scans, leading to more faithful reconstruction. Useful in diagnosis support, surgical planning, and prosthesis design through accurate surface modeling. Outperforms classical methods in terms of smoothness, structural fidelity, and computational adaptability. We try to apply the model generated by AI in the polygon of control of line, and this is the result. Finally, we conclude that the classical subdivision schemes provide a strong mathematical foundation for geometric modeling. However, fixed parameter methods are not optimal for complex, structure-rich data such as medical scans. We propose an adaptive learning-based subdivision approach that adjusts refinement according to local shape properties. Experimental results show improved visual and structural quality, especially in medical three-dimension reconstruction. Future work includes extending this framework to full three-dimension meshes and integrating domain-specific constraints. This is some reference. And finally, thank you for your attention.